Today we will see in detail about the exchange forces. If two particles are distinguishable and the particle A is at position x1 and particle P is at x2, then the total wave function psi of x1 x2 can be written as psi A of x1 psi P of x2. This is for distinguishable particle. If particles are identical, then this can be written as psi A sub plus or minus. Plus indicate symmetric and minus antisymmetric one. So which is equal to 1 over square root 2 psi A of x1 and psi P of x2 plus or minus psi A of x2. Now we are interchanging the particle and psi P of x1. So this is the total wave function. The plus sign is for boson, that is all particle with integer spins are called bosons, and it is negative for fermions. All particle with half integer spin are fermions. See, let us say for if you take this as a fermion, you will have minus 1. If particle positions are the same, that is a psi of A x1, psi of P x2, same thing is here. If you subtract both psi of A x1, psi of P, this will become 0. So that is according to Pauli exclusion principle. So fermion follows the Pauli exclusion principle, but not bosons. Uh, Now the expectation value of difference between position x1 and x2 whole squared is equal to expectation value of x1 squared plus expectation value of x2 squared minus 2 expectation value of x1 multiplied by expectation value of x2. First, we will see the square of the expectation value of the difference between x1 and x2 for distinguishable particle. For distinguishable particle, the wave function is psi of x1 x2 is equal to psi sub A x1 psi A sub B x2. That is, particle A is at position x1, particle P is at x2. So now the expectation value of x1 squared, this is a double integral, that is integral of psi modulus psi a squared with respect to tx1 and modulus psi b squared with respect to tx2. Now we have to find the expectation value of x1 square. So naturally we have to plug in into the first integral, because we are only first integral we are going to differentiate with respect to x1. This will be the second one. There is no x term. This is simply 1. This is equal to 1. Naturally, this is first one is expectation value of x1 square. This is purely due to particle A. So I am taking this as expectation value of x squared for a particle A. So I used sub A here. Similarly, what will happen for the expectation value of x2 squared? So here we have to plug the x2 squared in the second integral. So what about this one? As usual, this integral of psi star psi dx is equal to 1. So this will be 1. So this is the expectation value of x2 whole square. This is purely for particle P. So I am writing this as the expectation value of x squared for the particle P. So expectation value of x squared sub P. Similarly, the interactive term, expectation value of x1, x2 is equal to, now I have to plug the x1 in the first integral and the x2 into second integral. This will be the expectation value of x for the particle A. That's what I have written. This is the expectation value of particle P. So this is x per sub P. And now the expectation value of the difference between x1 x2 whole squared is this subscript t indicate the distinguishable particle, which is equal to this expectation value of x squared a and the expectation value of x squared p minus 2 times the expectation value of x a and the expectation value of x p. Now we will calculate the same thing for identical particle. That is square of the difference between x1 and x2, expectation value of the square of the difference between x1 and x2 for the identical particle. Identical particle we have plus sub plus or minus. So symmetric. If it is boson plus, if it is fermion then it is minus. So the wave function psi plus or minus is equal to 1 over square root of 2 psi a of x1 psi p of x2 plus or minus. Now we are interchanging the position, that is psi a of x2 psi p of x1. So you take the complex conjugate of this one, you will get this. Just you make complex conjugate of everyone. Now we have to find the expectation value of x1 squared. So the expectation value of x1 squared, there are 4 terms. Here you have 2, here 2. If you multiply, you will get 4 terms. One is self term. So this and this and this and this. And other two are cross term, this and this and this and this. So I can write this, if you multiply 1 over square root 2 into 1 over square root 2, that is psi star psi. You will get 1 over 2. Then I1, I2. If you multiply this, this is I1, this is I2. And cross multiplication is I2, I3 and I4. This is a cross term, you will get plus or minus. So I am using plus or minus I3 plus or minus I4. First you multiply this and this. So you can see is psi a star psi a, both are x1, position x1. So I can write that as psi a of x1 modulus square, this one. Then psi p star x2 psi b x2. Then that can be written as modulus psi p x2 whole square. Here both are at x2, so tx2. We are integrating this with respect to tx2 and this tx1. Now you have to plug in x1 squared here, because uh, this only contain all x1. So what about this term? This term is, as usual, this is equal to 1. So naturally the first integral is nothing but the expectation value of x squared for a particle A. This is for purely for particle A. So I am simply writing this as the expectation value of x squared for a particle A. Similarly this and this. What will happen? Psi a star psi a, psi which will become modulus psi a squared. Remember that here x2. So I have used the x2 and I am integrating over x2. Then second term psi b star psi b. So modulus psi b x1 squared. Then we have to plug in the x1 squared in the second integral only, not the first. So the value of this first integral is 1. Then the second integral is nothing but the expectation value of x squared. Here it is only particle p involved. So I am writing this as modulus x squared sub p. That is the expectation value of x squared for the particle p. Then we will see for cross terms. To find the I3, you multiply the cross term, that is this and this. What will happen? psi a star of x1, you group x1 because we are going to differentiate with respect to x1. Here psi p of x1, tx1. Then here psi b star of x1 and psi a sorry x2, psi b star of x2, then psi a star of x, psi a of x2, tx2. So here due to orthonormal property this will be 0, and I4 you multiply this and this. Then here you will get x1, you take psi b star of x1, then psi a x1, and next one is psi a star of x2, psi a star of x2, then psi b x2. Here this term due to orthogonal property this will be 0. So now the modulus x1 squared, expectation value of x1 squared is equal to half this I1, I2. I1 we know, just now we have seen expectation value of x squared per particle A, and I2 is the expectation value of x squared per particle P. I3 and I4 are 0. So you are just multiplying this. In similar manner, you can find out the x2 expectation value of x squared, x2 squared, which is equal to half x squared of A, expectation value of x squared per A, expectation value of x squared per P. You do the similar. This is lengthy process, but you will get easily this answer. You can realize from this fact. We got it for x1 squared is this one. So naturally x2 squared, expectation value of x2 squared also the same. So now we have to find the expectation value of interactive term, that is x1 f2. Already we have seen the expectation value of x1 squared and the expectation value of x2 squared. Here you adopt the same method, you will get 1 over 2 I1 integral 1 to plus or minus I3 plus or minus I4. So first I1 you multiply this self term, this and this. You will get here, remember that you will get psi a star of x1, psi a x1. So this will become psi a modulus psi a squared tx1 because both are x1. And here, uh, sorry, psi b star psi b x2. So which will become psi b square modulus psi b square tx2. Here tx1. So now you have to plug x1 in the first integral and x2 in the second integral. So the first integral will become the expectation value of x1 for a particle, single particle A. So I can simply write this as expectation value of x for the particle A. Same thing, this is expectation value for the particle P, expectation value of R. Then what will be I2? Just interchange this. First one is expectation value for P, second one is for expectation value of A. This is indistinguishable. So you can take AP, expectation value of A, expectation value of P. So if you add I1, I2, you will get 2 times this one. Similarly, what about I3, interactive term? Now you uh, multiply this and this 1 minute. So you multiply this and this. You will get psi a star x1, psi b x1. You group the x1, psi a star x1, psi b x1, and psi b star x2, psi a x1, psi b star x2, psi a x2. So now you plug in x1 here and x2 here. Now you can see this is the expectation value of x for the interactive term A and B. You cannot distinguish which particle in which position. So I can write this as the expectation value of X sub AB. Similarly here it is PA. So this can be written as modulus expectation value of x squared x sorry modulus I can write modulus expectation value of AB whole square. Similarly, this is I3. I4 also same. Here AB PA comes. Here PA AB. This is also for identical particle. It is nothing but the modulus square of the expectation value of x AB modulus square. Now, if you add I3 and I4, you will get 2 times this expectation value. So that 2, here 1, 2 you will get, here 1, 2 you will get. If you add all, then 1 over, outside you have 1 over 2, that 2 will get cancelled. You will get modulus x1, expectation value of x1, x2 is equal to expectation value of A, this one, expectation value of P plus or minus this modulus square of the expectation value of X due to particle AB. So this is the interactive term. Now we will move further. We have seen the expectation value of x1 squared is equal to half the expectation value of x squared for the particle A plus the expectation value of x squared for the particle P. And similarly, we have seen that x2 squared, expectation value of x2 squared is also the same. Now, also we have seen the expectation value of x1, x2 is equal to the expectation value of x for particle A and the expectation value of x for the particle P plus or minus the expectation value of modulus square of the expectation value of A particle AB. So now what is uh, the difference in the position, difference in square of the difference in position for identical particle, the expectation value of square of the difference in the distance between particle 1 and 2 is equal to this by definition a minus b whole squared is equal to a squared plus b squared minus 2ab by definition. So here this a squared plus b squared, if you add this and this you will get this half will go away, so you will get the expectation value of x squared for the particle A plus the expectation value of x squared for particle P minus this one 2ab. This will become minus 2 expectation value of x for particle A multiplied by the expectation value of particle P. Here this plus or minus, because we are subtracting this will become minus or plus. That is important. Minus or plus 2 times this expectation value of x for the particle AB modulus squared. So you will get this I can simply write instead of writing x1 minus x2, this is delta x. That is a difference between the distance x1 and the x2. So the expectation value of delta x squared is equal to this one. This we have read. Already we have seen same thing for distinguishable particle, that is expectation value of x1 minus x2 squared is equal to, here this also we can write as delta x. So I can write this is expectation value of delta x squared for distinguishable particle. We have seen this. This is exactly same as which I have shown in blue color rectangular box for the case of identical particle. So here I can replace the first three term by first I am replacing this expectation value of delta x squared plus sub plus or minus, then this blue color is exactly same as the expectation value of delta x squared for the distinguishable particle. Then this extra term is only minus or plus 2 times the expectation value of x ab modulus squared. So here for boson is I have told that it is plus for boson and minus for fermion. Here due to this minus it become minus or plus. So upper sign is for boson and lower sign is for fermion. So if you subtract this from this, then in the case of identical particle, this distance is closer. And for for boson it is closer because minus sign. For fermion, it is far away comparing this delta x square, my expectation value of delta x square of plus or minus. So this is closer for boson and apart for the fermion. Thank you very much for watching my video and supporting me continuously. Thank you very much.